And welcome, students and teacher. This is our last of the AP Chemistry content review sessions. And I'm Lew Acampora, the Science Director for Advanced Kentucky, but also I'm an AP Chemistry exam leader, and I'm involved in the writing of the exam and the proofreading. So I know what's going to be out there, not in the specifics, but what you're likely to see, especially this year when things are so unusual. And I hope that this will help you a little bit. I'm going to just scroll through this quickly. We have just a handful of students here, so do feel free to use the chat box liberally, and my co-host will let me know when there might be a question. But I don't want to bore you or review too much material, so I'm going to try to go through this as expeditiously as possible. Okay. This and all other sessions are archived at kyap2020.com, and I will post some notes that I will refer to today. So the topic of today is chemical equilibrium, and this is an important topic. This is really kind of traditionally the culmination of AP chemistry, and before we get too into the weeds with it, I want to talk about, why is this important and what is equilibrium? And most of us, you study chemistry and you start learning about reactions, and maybe you're in introductory chemistry or a pre-AP chemistry course. And we know that for most reactions, you start out with some reactants. Well, this is why I need to get a, and they react and they turn into different stuff and they form products. And we describe these chemical reactions with correct equations and balanced reactions to show that atoms are neither lost nor gained. And this arrow tells us that something interesting happens. And this happens until we run out of a reactant. So, for example, let's say we were to react hydrogen gas. And I'm going to be a little bit brief in my notation here. And oxygen gas. Remember, oxygen and hydrogen are both diatomic as elements, and they will, of course, react to form water. This is a fairly enthusiastic reaction. Anyone who's seen the video of the Hindenburg going up knows that it happens very, very quickly and very exothermically. This is not balanced, of course, so we'll go ahead and balance this, and there are lots of ways we can balance it. Oh, I'll find some nice pink letter numbers here. We'll put a 2 here and a 2 here. And you don't have to, but I'll write a 1 there. And this tells us that the hydrogen, oxygen react in a 2-to-1 ratio, not of grams, but of moles. And remember, this is the important fact about AP chemistry, is that you've got to get used to using this unit of moles, because in chemistry, things happen in ratios of numbers of particles, not necessarily ratios of grams or milliliters or things like that. And that's why being able to convert to and from moles is so important. So regardless, we've got this reaction, this now balanced equation, and we might take our container, and we'll make this container happen at a constant volume. So we've got a rigid container, and we'll go ahead and put some hydrogen gas in there. These little dots will represent hydrogen. Hang on, I wonder if I can do this. Okay, so those are hydrogen molecules. And then we'll go ahead and put some oxygen molecules, and we'll choose a nice blue color for oxygen. Oh, I should have saved blue for water. Okay, well, that's okay. And as this reaction takes place, we know that the balanced equation says that we'll get rid of 2 hydrogen molecules and 1 oxygen molecule and replace it with 2 water molecules. Oh, I need my pen for that, don't I? Oh, those colors aren't too different, but you can see that with it. And this would happen. And the fact that I've got an arrow here tells me that this would happen until we run out of some reactant here. So if I had some number of moles, and for reasons we'll see in a little bit, we usually want to talk about the concentration. So we can assume this has got a volume of 1 liter. Be careful on a question, because if the volume is not 1 liter, you'll have to change for that. And also we'll assume this is happening at some constant temperature. Now we know this reaction is very exothermic. It gives off a lot of heat energy. So, but we'll assume that this heat energy goes through the container, that this is not a very well insulated container. And the fancy schmancy word for that is we assume that the walls of this container are diathermal, and diathermal means heat can transmit through them. So if I had some amount of hydrogen at some concentration initially, and I'll just make up some numbers here. Let's say we got 0.4 moles per liter, and I might start out with 0.3 moles per liter of oxygen and have no water at the beginning. And notice, and some students are confused because they think that I've got a 2-to-1 mole ratio here. I better have a 2-to-1 mole ratio here, but I'm the chemist. I can put in whatever I want. It's not that I need to start with that ratio, but when they react in that ratio. So my change in concentrations will be in a 2-to-1-to-2 ratio. And in this case, my hydrogen is my limiting reactant because even though there's more of it, it's used up twice as quickly. So I use up 0.4 moles per liter of hydrogen, and I use up half that number of moles per liter of oxygen. So half of 0.4 would be 0.2. And I would produce the same number of moles per liter of water as I consumed hydrogen. That's a 2-to-2 ratio. So I'm going to put a plus 0.4 here. And that means when this reaction is done, here's my final state. I'll have used up all of my hydrogen, so there's none left. I've still got 0.1 moles per liter of oxygen that has remained unreacted. And I form 0.4 moles per liter of water. And this is typically what you would have seen. And I think everyone listening can do this. And I encourage you to set that up. It's just, fundamental chemical stoichiometry, or the ratios of quantities. And this is what happens, a reaction chugs along until we run out of a reactant. And we call that reactant the appropriately limiting reactant. Why does that happen? And that's what we show on this diagram here. So I'm going to go ahead and save that screen and then erase it. And this happens when the products have much, much lower energy than the reactants. And you can think about this vertical axis as an energy curve. Most of the classes haven't gotten to the distinction between enthalpy, or the heat that you might have measured, and this G thing, which is called free energy. That's actually Unit 9 for AP Chem. So you won't probably get to that this year, but when you take college chemistry, it's fascinating, and I hope you do get to look at that. But the point is that once reactants have become products, have converted to products, they've gone over this energy hill, and from kinetics, you might recognize that as the activation energy. And now they're at a much, much lower state of free energy, what we would call a thermodynamic sink, which means once they've gotten here, there's no way they're going to climb this hill and be able to convert back into reactants. So these reactions are irreversible when the change in energy of the reaction is much, much less than 0. And in practical terms, this is really probably less than -100 kilojoules per mole. Kilojoules per mole. The opposite, and so here's where we had 2H2 plus O2 going to 2H2O. The opposite, if we kind of flip this graph along the vertical axis, if we have the reactants are much, much lower in energy than the products, then there's no way that this reaction is going to occur, certainly not occur spontaneously. We can make it happen, and if you've ever done an electrolysis, if you can supply a steady source of energy, you can have this reaction occur. And we could take water and we can electrolyze it, use electricity to split it into hydrogen gas and oxygen gas. And if we can actually use solar energy to do this, that would be great, because we could reduce our dependence on fossil fuels. But just the opposite of this, we've got a delta G naught that is very positive. The equilibrium happens when the reactants and the products are comparable in energy. They don't have to be exactly equal, but if the reactants and the product side are very comparable in energy, then we get this situation where neither is strongly favored thermodynamically over the other, and our lowest free energy configuration has some mixture of reactants and products. And a similar example here might be if we had the reaction of nitrogen monoxide, NO, plus oxygen gas, to form NO2, nitrogen dioxide. So I'm going to move my picture out of the way. And I'm going to balance that here and here. And to show there's equilibrium, we usually represent this with a double-headed arrow, or an arrow that goes both ways. And this says that we reach a state of equilibrium, which means that if we were to start with, get rid of that, let's say we were to come back here and start with our container with initial concentrations, and I'll use the same initial concentrations as earlier. Notice this equation looks very similar to the one I had written earlier with the hydrogen. I've got 2 particles reacting with 1 to form 2. And if I start with 0.4 moles per liter here, and 0.3 moles per liter here, and none here, well, now this would chug along and they would react, but as they, and that there would be this arrow here. So if you think about your chemical kinetics, the rate of this forward reaction would depend on the concentrations of these 2 reactant species, depending on the rate law, not necessarily second or first order, but there would, as these concentrations decreased, the rate would decrease. But now there's a reverse reaction that can occur. And initially the reverse reaction can occur because there's no product, but let's say I wait a little bit, and now this might be down to 0.3. And these are the calculations that it takes practice, but you should be able to do quickly. Since the concentration of NO went down by 0.1, this concentration is going to go down by 0.05, half of that, which leaves me with 0.25. And I'm skipping some steps here, but I think you can all follow that. And this concentration will go up by 0.1, from 0 to 0.1. And now at this situation, under these concentrations, the forward reaction is slowed down a little bit. I'll try to draw a slightly shorter arrow here. But now the reverse reaction is actually taking place, because now I have some product that can climb this much smaller energy hill than over here, comparable, and is going to, now, according to this diagram, the forward reaction is still proceeding more quickly than the reverse reaction, so this concentration will continue to increase. I'm going to draw 2 up arrows there to reflect that coefficient, while this concentration decreases, as does this concentration decrease with 2 down arrows, because there's a 2 there. But eventually, as this reaction chugs along, as the system evolves, these reactant concentrations will decrease, the product concentration will increase, until I get a situation where this might be 0.24. And you should all be now thinking very quickly, what will I fill in for these other concentrations here and here? So I'll give you a moment to think about that. And rather than wait for the chat box, we'll move along expeditiously and say, well, this decreased by 0.06. So that's going to decrease by 0.03 to 0.22. And now it's going to increase by 0.06 to 0.16. And if this is the state at which these 2, the forward and reverse reaction, are occurring at the same rate, then these concentrations will not change. I've reached a state of equilibrium. And that's why it happens. And I might even label this concentration at equilibrium. So I haven't run out of there's no real limiting reactant, but what I have is a state where it's going to be at equilibrium. Let me save that and say, how can we mathematically describe this state? I think I've got to annotate out of that, and then, whoops, there we go. And now I want to annotate again. So I'm going to clear that. So two quantities you need to be familiar with is, how do we describe that situation? And I'm going to go ahead and put that back up here. 2NO plus O2 in equilibrium with 2NO2. Pardon my handwriting's bad enough, and using the little trackball is even harder. So I had equilibrium concentrations of oh, no, 0.24, 0.22, and 0.16. So remember, at equilibrium, the forward and reverse reactions have to be occurring at the same rate. And Wendy, I can't see the chat box, so if there are any questions out there, please feel free to interrupt me, and I'll try to address them as best I can. I know I'm going through this pretty quickly. We want to mathematically describe the state of equilibrium, and we do that with the equilibrium constant, and that usually has a symbol capital K EQ, and it could be different. Sometimes we'll have a different letter down here. It might be A for an acid dissociation, or B for base, or P for pressures. So this is just a general term. And it's always going to be the concentration of products raised to their appropriate powers, the stoichiometric power. So in this case, I get 0.16 squared over the product of the reactants, and that's what this symbol here means. So it'd be 0.24, which I would square because of that 2, and then another factor of 0.22 in the denominator. And this is the expression. Well, I didn't really write the expression. I plugged in the numbers. But you should be able to translate from an equation to an expression, and we'll look at some pitfalls to avoid there. If we go ahead and calculate this numerical value, and I'm going to do this very quickly with my calculator, although I don't really need one because 0.16 over 0.24 is 2/3, and when I square that, I get 4/9, and 4/9 divided by 0.22 should be about 2, and I get 2.02. Okay, so there's a value of 2 there. So this would be the value of the equilibrium constant. What does this tell you? Well, it says that I could have a lot of different sets of concentrations that would satisfy this relationship, but whenever that is satisfied, the rates of the forward and reverse reactions will be equal. And that's merely my criteria, my kinetic criteria for equilibrium. So, you should be able to look at a reaction and if you know the equilibrium concentrations, you should be able to plug them into the expression for the equilibrium constant and get a value. Conversely, if you're given a value and some set of concentrations, you should be able to solve for the other one. Generally, I might have arbitrary concentrations. So let's say I've done this, and I'm going to mention 2 things. The value of the equilibrium constant does depend on the temperature. So if you change the temperature, the value of the equilibrium constant will change. Not the expression, but the value. The value, well, what are the range of possible values for the equilibrium constant? Clearly, it can only be a positive number. You can't, so many numbers in chemistry can be negative, delta H values, or cell potentials, or things like that. But equilibrium constants, because there are ratios of pressures or concentrations, and all of these have to be positive. So equilibrium constants are always going to be positive, but they can be very, very small numbers. 10 to the -15th, 10 to the -20th are perfectly meaningful, or conversely, very, very large numbers. The bigger the value of K, the more strongly the numerator, which represents a product concentration, is favored over the reactants. And so if you can imagine K being 1 or very close to 1, then my reactants and my products have comparable concentrations. But if K had a value of 10,000, then I would know that at equilibrium, the products would have a higher concentration than the reactants. The other thing that I should be able to do for this, and this we'll see it when we look at the behavior of equilibrium systems. Let's say I'm given the same reaction, but a completely different set of concentrations. So I have some system here where, well, I don't know if it's at equilibrium, so I'll just put a question mark here. And I've got, this might be 0.4. Boy, that green's a pretty ugly color, sorry about that. And this might be 0.1, and this might, the NO2 at this instant might have a concentration of 0.03. I'll try to make these numbers easier. Is this system at equilibrium? Well, unlikely, because I just made those numbers up, but how would I check? And I would plug these concentrations into my equilibrium expression. And when I did that, I would get 0.3 squared, that's a decimal point there, over 0.4 squared times 0.1. And when I do the arithmetic on that, let's see, 0.3 over 0.4 is 0.75. And I'm going to go ahead and square that and then divide by 0.1. I get a number of 5.6. And 5.6 is clearly not equal to 2. So I know I'm not at equilibrium. But more importantly, or not more importantly, but I can be a little bit more specific than that, 5.6 is bigger than 2. So this system will evolve to lower this value of Q, the reaction quotient. I wouldn't call this the equilibrium constant because it's a different, but it represents the state of the system under these concentrations. And to lower this, the value of Q, I've got to lower the numerator and increase the denominator. And I'm going to get rid of that green. You guys are very tolerant of that. Have it a nice brown. And that means this is going to decrease. And I'm going to actually put down 2 down arrows here because the stoichiometry here is non-negotiable. It's always going to be a 2 to 1 to 2 mole or concentration ratio. And this will increase, and this will increase by twice as much. So as this, if I started out with these non-equilibrium concentrations, as the system evolved to equilibrium, I know the concentration of NO2 would decrease and the concentration of O2 would increase and the concentration of NO would increase by twice as much. I said a couple of pitfalls to avoid, and okay, just a personal, when I was in high school in 9th grade, I took introductory Latin. Back in those days, I actually taught Latin in schools, many schools, and my Latin 1 textbook always had this little box at the bottom of every section that had pitfalls to avoid. And I don't remember what they were, but I do remember the box. So that's why I say pitfalls to avoid here. These quantities are concentrations, not amounts. And that means if you have a solid or a pure liquid or a solvent like water whose concentration is not going to change, then it's omitted from the equilibrium expression. And I know that you are very likely to see that. So if we had something where you were in water solution and you had some acid in equilibrium with its, well, I should write my plus H2O here, otherwise this won't make any sense. Going to hydronium ion plus a conjugate base. Then the equilibrium constant expression for this would be the concentration of hydronium ion over the concentration of the conjugate base divided by the concentration of HA, but we wouldn't include the water because it's a solvent, it's not going to change its concentration. Okay, so moving along, I think. Oh, there we go. Oh, we already talked about this, so I'm going to skip over that and talk about the behavior of equilibrium systems, which I really kind of talked about already. So let's do that. And this is LeChatelier's principle, and this is really what differentiates equilibrium from just kind of normal stoichiometry, but from just the limiting reactant that you've seen before. If you can imagine going back to the system we started with, where you have hydrogen and oxygen reacting to form water, and let's say we had that box, that cylinder, and we had in it some hydrogen. Well, we started with hydrogen and oxygen, and we end up with water, and I'll be a little bit smarter this time. I'll make water molecules, my nice blue color here. And if we happen to have some oxygen remaining, where the green dots represent O2, and those blue dots represent water molecules. Well, if I were to put more oxygen in there, nothing would happen. I've got plenty of oxygen to begin with. There's no hydrogen there to react with. I could add more oxygen, and all I would do is increase the amount of oxygen there. Or I could take out some water and nothing would change except I would remove the water. Or I could put in some hydrogen, and if I were to now take and put in some more hydrogen, like those red dots represent hydrogens, it's so nice and flammable. Then once I had some red dots in there, I would react, and two of my red dots, would react with one of the blue dots, or one of the green dots, the oxygen green dots, and would form two blue dots. And pardon my here. So if there's no equilibrium, then nothing really interesting happens. Let's imagine what happens when we do have a system at equilibrium. And I'm going to go to a whiteboard here, which will make this a little bit easier. And I'll go back to the same system we had earlier, where I've got two nitrogen monoxide molecules, and these are all in the gas phase, reacting with an oxygen molecule to form 2NO2. And we'll say we start with our system and it's at equilibrium. So, oh gosh, now I've got to remember back, but I think this was 0.24 and this was 0.22, and those are concentration in moles per liter, and this was 0.16. And these are our equilibrium concentrations. And using those values, the expression for KEQ is going to be the concentration of NO2. And as you write these, make sure you're pretty careful about writing formulas inside the brackets and exponents outside the brackets. Students always, or some students frequently mess up because they'll put this 2, which should be the exponent, inside the brackets. And this particularly gets even more challenging, and you've got to be more careful when these are particles in aqueous solution that might have charges. So make sure the brackets refer to the concentration of the species. Remember, this 2 is not part, this coefficient does not go in front here. We're talking about the concentration of NO, not the concentration of 2NO. So you really got to think carefully about that. And I know as you are taking an exam, you might be a little bit flustered. But it's worth practicing. And remember, for these numbers, we had a value of 2.0. And I got that number by squaring that and dividing it by that squared and that squared. I can try that. Look at that, squaring that. Now, what does LeChatelier's principle say? Well, it says that if I have a system at equilibrium and now I exert some stress on it, and that stress could be adding a reactant, or I say adding, I really should be more precise and say increasing the concentration of a reactant, because if one of these were a solid and I were to add more of it, that wouldn't be changing its concentration and nothing would change. And a simple example for this, for those of you who like really, really sweet iced tea in the summer, and if you pour in enough sugar that no more of it will dissolve, and there's a layer of solid sugar in the bottom of your iced tea, and well, you could keep adding as much more solid sugar as you want, but no more of it is going to dissolve, because even though you're adding more iced tea, you're not changing its concentration. So we want to make sure, in fact, I'm going to take just a minute here and put G here for gases. And while I'm doing that, I also want to remind you that when you have a gas phase reaction and it's being carried out at constant temperature and constant volume, you can, which these typically are, you will not see an AP Chem question that that doesn't happen, that you can use pressure as a stoichiometric variable. So I could also talk about these as being pressures in atmospheres. When that happens, we usually call this a KP. But for now, we can imagine these are, we stuck with moles per liter, and we'll keep going that way. Let's say
Hey, Lou.
Yes.
Since you mentioned KEQ, this is Monique.
I recognize you, Monique.
Wendy posted a question in the chat. Is KC the same as KEQ? A student asked me, and I thought it would benefit the group.
Yes, I'm glad you asked that. And as I said, yes, KEQ is kind of a general equilibrium constant with lots of, just as we say that mammals include dogs and cats and cheetahs, and I think cheetahs are mammals, I guess it would have to be, and so forth. So KEQ would include among them KC, and that C refers to concentrations. So we could also call this a KC. It could be a KP, where P is pressure. It could be a KA, and KA, the A there stands for acid. Could be a KB, and I'll let you guess what B stands for. Base. Could be a
Base.
KSP for good. So these are all in that. And I could just as easily call this a KC because I'm talking about concentrations here. And these are concentrations. I left off the unit here, but they are in mole, they're all in moles per liter. But that's a good question. There are technical differences between them. This is not anything you're responsible for in the AP Chem curriculum. So if you were in a graduate level thermodynamics course, you would be concerned about the distinction, but they're not going to try to trick you up here. Use the value that is appropriate and labeling aside. So here we have the system, and we're at equilibrium, and that means that the forward and reverse reactions are chugging along at the same rate, so these overall concentrations are unchanging. Let's say we go in and we change one of these, and Monique, are you listening?
I am.
I'm going to let you tell me which one to change and in which direction and by how much.
No, you're not. Please don't ask me that.
Let's pick one of these three things.
Pick one.
Pick one.
The oxygen.
And should it go up or down?
I don't know. Up.
Let's go make it go up by 0.1 moles per liter. So we're going to take, and we are going to take the hand of God, Deus ex machina, and we're going to increase this by 0.1 moles per liter. And that means that until, if nothing else happens, something will happen, but before that happens, I'm just going to add my 0.1 to my 0.22 and get 0.32, and this won't change. So my concentrations of NO and NO2 didn't change, but I just somehow took my system and I injected more oxygen gas in there. Is this now at equilibrium? And every student out there should be, and you don't have to type it in the chat box, but should be thinking a resounding no.
No.
And there are two reasons for that. Well, there's one real reason, but we can look at it two ways. One is, well, look, I had this situation here where these concentrations, this quotient equal 2, when I make this number bigger, when I make that number bigger by essentially a factor of 50%, that's going to reduce this from 2 down to 1.3 or so, which means we're not at equilibrium. If you like kinetics, you might say, okay, I had a situation here where the forward and reverse reactions are occurring at the same rate. I increased the concentration of reactant. Since the rate of the forward reaction depends on the concentration of reactants, that's going to increase the rate of the forward reaction, but I haven't done anything to change the rate of the reverse reaction. So I had a situation here where two things were equal. One of them increased, the other didn't, so they're clearly no longer equal. And that means that this is going to, the reaction is going to proceed in this direction here. And as I approach equilibrium, this concentration will increase by 2 factors of X, and this one will decrease by 1 factor of X, and this one will decrease by 2 factors. And the number of arrows represents a stoichiometry here, that 2 and that 1 and that 2. Now, you will never need to do this on an AP exam, but you could go ahead and figure out what the new equilibrium concentrations are by adding 2x to this, subtracting an x from that, and subtracting 2x from this. And then my equilibrium concentrations here would be 6.16 plus 2x 0.32 minus x and 0.24 minus 2x, and I could plug those into this expression up here, set it equal to 2, use my calculator, my computer to solve a cubic equation and come up with a value of x. You will not need to do that. But you do need to interpret what's, because all the chemistry is done now. Now it's just a math problem, not to speak ill of math. We all know and love it. Love it anyway.
Yes, yes, do not speak ill of math. You know I'm here.
I know. But what would LeChatelier say? Well, LeChatelier would say, okay, I've got a situation equilibrium. I have stressed that equilibrium by increasing the concentration of the oxygen. The equilibrium will shift in a direction that will use up some of this, that will reduce this. We'll use up some of the oxygen that I added, but in using up some of the oxygen, it is bound by the non-negotiable coefficients here. So as I use up oxygen, I also need to use up nitrogen monoxide and nitrogen dioxide. And that's a common application of LeChatelier's principle. I want to do it's 3 other stresses, and I could probably finish our time together because you guys have been so good. Let's say that instead of increasing the concentration of oxygen, which drives this reaction to the right, or if I were to somehow put more NO2 in there, the reaction would shift back to the left, and you could imagine all of those. Let me erase this and imagine another stress on the system. And since this really only works for gas phase reactions, but let's say I were to take my system, and here it is, and I've got and now I'm in this cylinder with a movable piston, and I've got my mixture of species in here. So I've got a few of those, and I need to have some other color in there. Oh, that purple looks nice here. And now I were to take and change the volume. So I'm going to take now and take my cylinder and just push this down. And just to make it concrete or specific, let's say I have the volume. And since these are all specifically ideal gases, and you know about the ideal gas law, when I have the volume, and now all of these particles are down here, I double the concentrations, I double the pressure, and I double the concentrations. I've got the same number of moles and half the volume. So this becomes 0.48. This becomes twice 0.22, and that's 0.244, and this becomes 0.32. And the question is, the usual question is, am I still at equilibrium? And if so, or if not, in what direction will things happen? And it's very tempting to say, well, look, I've changed all of these concentrations proportionally, so there's no overall change in the system. But why would that be incorrect? You don't have to answer that, but I want you to think about it for a minute. So even though every one of these concentrations has changed by the same factor, they've all gone up by a factor of 2, the value of the reaction quotient Q has changed because now I've doubled the numerator, or I've doubled the concentration in the numerator, but I've squared that, so the upstairs in this fraction has gone up by a factor of 4, but the downstairs in this fraction has gone up by a factor of 4 times 2, or 8. So now my value of Q is actually 1, which is less than 2. How's that for good math? 1 is less than 2. So, but we're not very happy at 1. So this system will evolve to increase the value of the quote. So let's see. So 1 is less than 2. We want to increase the value of Q by forming more product, by increasing the concentration of product, and decreasing the concentration of reactant. And there I go with my arrows again. Now, as I said, what would LeChatelier say? Well, he would say, okay, I had a system in equilibrium. I have now perturbed that system by decreasing the volume by a factor of 2, which immediately doubled the pressure. The system would like to shift that will, in a way that will reduce or attenuate the change in pressure. Since I have 2 moles of gas on the right and a total of 3 moles of gas on the left, I could reduce the pressure by having the reaction occur in this direction, because I'm going to take 3 particles and turn them into 2 particles, which according to the ideal gas law will reduce the pressure. So, this is another instance of LeChatelier where an increase in pressure will favor the side with a fewer number of moles of gas. So, if this were reversed, well, the reaction would go the other way. So then, that's another way for a gas phase reaction, perturb your system. Again, we're starting with equilibrium, and then we're doing a change on it. And this really only is applicable for gas phase reactions. Notice that neither a change in the concentrations of reactants or products or a change in the volume changes the value of the equilibrium constant. The value of the equilibrium constant at this temperature is still unchanged at 2. We'll look at 2 more stresses. Wow. And this does come up on the AP exam very frequently, almost every year, well, probably every year. What else can I do to the system is I could change the temperature. Remember, we even though this reaction may be exo or endothermic, we're assuming it's happening in a container that is in thermal equilibrium with its surroundings. So if it releases energy, that heat gets dissipated, or if it takes in energy, there's a reservoir of energy. What if we were to take that temperature and increase it? So now we're going to take and make the temperature go up. Well, that is going to change the value of the equilibrium constant, but it's not clear whether the value of the equilibrium constant will go up or down. Now, I will tell you, and we'll kind of do this. Let's assume, well, this reaction, in fact, is exothermic. So you've got to know whether this is a exo or endothermic reaction. And remember, saying this is exothermic is synonymous with saying that the delta H of this reaction is less than 0. And that if we were to run this reaction in an insulated system, the temperature would go up because it's releasing heat. So it turns out that if the temperature increases, if we externally increase the temperature of the system, well, think about heat as a product of this reaction, and increasing the temperature will increase the availability of thermal energy. And since I'm really increasing the amount of product heat as a product, that's going to drive this reaction to the left. So if I increase the temperature, I would expect that these concentrations will decrease, and now this concentration will increase, and this concentration will increase by twice as much when I get to my new equilibrium. I want to be careful here because another really tricky thing is saying, well, what does that mean in terms of these reaction rates? And even though increasing the temperature will shift the equilibrium to the left, it's actually going to increase both the forward and reverse reactions. Reactions always speed up when the temperature increases, but in this case, it will increase the rate of the reverse reaction by more than it increases the rate of the forward reaction. So, don't be tricked into saying, well, as you increase the temperature, the rate of the forward reaction decreases. It doesn't. It will actually increase because there are going to be more particles that can form that kinetic energy, or chain that activation energy. But the reverse reaction will increase by a greater percentage or by a greater proportion.
Mr. Acampora?
Yes.
I have a student that has a question. Is temperature the only thing that will change the value of Kc? I thought this might be another one that would be good for the group.
Yes, temperature, the value of the equilibrium expression, whether it's Kc or Kp or anything, is temperature dependent. But, well, I'm going to say that for a given reaction. And I'm glad you asked that, Ms. Rader, because sometimes we could write the same reaction and we could write it in different ways. So remind me, I've got one more thing to talk about, and that's catalysts, which won't take very long. But let's say I were to take this same reaction. And now I'm going to put a number here. And let's say the delta H value here is equal to negative 60 kilojoules per mole. And that's kilojoules per mole of reaction. Let's say we're to take this exact same reaction, but write it slightly differently, where I want to know what happens if I have only 1 mole of NO. And this means I'm going to have to balance it with a half mole of oxygen. And there are good reasons you may want to write this like this. And sometimes we start out and we say these coefficients have got to be integers, but I'm not that dogmatic. And so this is still a balanced equation. I've just divided all the coefficients by a factor of 2. The delta H for this reaction as written will be half of what it was. So it will be negative 30 kilojoules per mole. And remember, that's because it's 30 kilojoules per mole of reaction. And in this second case, a mole of reaction involves half as much stuff. What would the value of the equilibrium constant for this reaction be? Well, if I think about it here, if I took this expression from the first reaction, I'll put a Roman numeral 1 here. For the second reaction, I would have the same thing, except all the coefficients would be half as big. So I'd have NO to the first power over NO, or NO squared to the first, NO2 to the first over NO to the first times the square root of O2. So the equilibrium constant here would really be just the square root of KEQ. I'll put Roman numeral 1 here as for this equation is written. So when I change the equation for the reaction, the value of the equilibrium constant changes. So I'm not sure if the student intended to ask that question. I hope you take credit for it though, because it's a great question. You might also think what happens if I were to flip and write, since this is a reversible reaction, I could write this as NO2 decomposes to form NO plus 1/2 O2. And that's pretty nice. But if you think about what happens if I were to write out the equilibrium expression, the numerators become the denominators and the denominators become the numerators. So I would just take the inverse of this, and I would take 1 over the value of the equilibrium constant. But in terms of changing the value without changing the chemical equation, yeah, a equilibrium constant has a given value at a given temperature. And when you talk about delta S and delta H, you can actually predict how that changes. But LeChatelier's principle is some application to know. And finally, and I'm going to have to run here because the AP Biology mock reading is starting in 5 minutes ago, but that's okay. Let's say, finally, and by the way, I'm happy to get back again with a group. So, if there are any lingering questions, Ms. Rader or any of you students, do feel free to email me, and I'm happy to Zoom chat with you all. My email is lacampora@kscc.com, and it's on our information. Let's say I had a situation, and now I were to do something like add a catalyst. And most of you know a catalyst will speed up a reaction without being consumed. What effect would it have on the equilibrium? And the answer is absolutely none, because adding a catalyst will increase the forward and reverse reactions proportionally by reducing that energy barrier. So if I'm going from there, and now it's here, but it won't change the value of the energy difference between reactants and products. So adding a catalyst will not change a system that's already at equilibrium. Now, if you have a system that's not at equilibrium, adding a catalyst will get it to equilibrium a whole bunch sooner, a whole lot faster, but it will not change the value of the equilibrium constant. And I think that pretty much will cover most of LeChatelier's principle. I'm going to save this and post those to our website. But other than that, I hope this has been helpful for you. Yep, you've got my email there, and I do love hearing from students, and I will be happy to Zoom with you. I've done private Zooms. I'm not a man of the millennium, but I'm learning. But I will say goodbye now, and thank you all for being here. And really good luck on the AP Chem exam. I think it's a great course. That shows, and it's worth working hard at. Okay, any final
Thank you, Ms.
questions?
Acampora.
You're welcome, Ms. Rader. Nice to see you students there, and good luck and all. Bye-bye now.
Bye-bye.